Under optimal conditions, the growth of a certain strain of bacteria is modeled by the law of uninhibited growth. From numerous experiments, it has been determined that the doubling time of this organism is 20 minutes. Suppose 1,500 bacteria are present initially. Find the exact value of K, the growth constant, and follow up with how long until there are 10,000 bacteria, rounding your answer to 1/10 of a minute. Okay, so first off, we need to know what formula to work with. This can be written in lots of different ways. Depending on the book you use, you might have Q of T equals Q naught e to the KT. You might have A of T equals A naught e to the KT. N of T equals N naught e to the KT. But they're all the same as our basic PERT formula of continual growth. So I just work with this basic one. It doesn't really matter. R is K is whatever. They want to find the exact value. I'll give them exact value regardless of which one we use. So I just stick with that one, but it's up to you. So we have, first off, the half-life. Oh, sorry, the doubling time. Doubling time. So for doubling time, technically, it should be P and 2P. If you wanted to do it with, it doesn't matter how much you start with, it'll double after 20 minutes. But a lot of students don't like to do it algebraically like this, so you could just stick with, it doesn't matter, like the 1500. That's fine as well. If I run it for 20 minutes, it'll double. That's fine too. Either way, to solve for the R, the growth constant, they're calling K, R, whatever, you need to get rid of this coefficient. Up here, if you were to divide by P, whichever way you do it, you end up with this, 2 equals e to the 20R, or K, depending on which one you use. Natural log both sides allows us to eliminate the E, and we now have, I didn't change colors, there we go, natural log of 2 equals 20R. So we have R equals natural log of 2 divided by 20. That's the exact value of the growth. Now I'm not including the R equals because they had a K, whatever. That's the value of the growth constant. Don't approximate it, please. If you do, you'll make rounding errors later on, specifically in part 2. So we now have a more specific formula. We now have A equals 1500 e to the natural log of 2 over 20 times T. That's actually the formula for our specific bacteria strain. So that's the part we'll use in part B. How long until there are 10,000 bacteria? Starting with 1500. With this, and I'll just use R. I know what R is, and I'll use that when I get my final calculation, but I don't want to keep writing it when I can just write R with an R equals already known. Same basic steps. Solve for T. Get rid of the coefficient. So that's 10,000 divided by 1500 equals e to the RT. Then natural log both sides. I'm not even simplifying where I could because the calculator is going to do all this for us. And we know R, so T is 1 over R, natural log of 10,000 over 1500. So to get to the nearest minute, first off, we had ln of 2 divided by 20. Let's work that out. This is the rate constant, growth rate constant. So it's about 3.46%, but I'm not rounding this. I just put it in there, so it's now in the answer button spot. We have natural log of 10,000 divided by 1500. All that divided by our growth rate, which I have in the answer button. 54.739 to the nearest tenth, 54.7 minutes. Okay, as far as the unit minutes goes, all the way back up here, by using the 20 minutes, the growth rate is now a per minute rate. So this R is per minute. And so by using this R, which is per minute, we get the time as minutes. Okay, that's it.